Okay, in class we looked at organic reactions, and I said that this was a video that was entirely optional, but would go through a few more details, and if it helps you to know what's going on, and if it helps you to do the reactions by knowing what's going on, this is going to go into a little bit more detail. So a couple reminders. We want to focus on the functional group. I often hear people saying that this reaction turns this into that, and it really isn't a magic trick. It really isn't anything being, alkene being turned into an alcohol. It's a reaction, and maybe water is being added across a double bond. And it's always helped me to talk in terms of what's actually happening, and it's also always helped me to understand what's going on at the molecular level. So I thought if it helps you, then we'll take a couple of minutes to do that. Okay, so the first reaction we looked at was what's called electrophilic addition, and that just means electron loving. So anything that's electron loving means you have to have something that, well, what loves electrons? Electrons are negative charge, so a positive charge. Okay, so what we have in that possibility was we had a double bond where something was being added across a double bond. The electrons moved from where they had been shared into new sharing positions. And I could have the hydrogen chloride being added across a double bond in this way, or I could do exactly the same thing with it lined up the other way around. Now, we talked in class in the previous video about the possibility of preference being shown, Markovnikov's rule, and we're going to take a quick look at that. So here's the thing that's actually, I guess I got the whole thing up there, why not? Okay, so electron loving, something that is positively charged. Well, the hydrogen in the hydrogen chloride actually has a slight positive charge, so the electrons of the double bond are attracted to that. So once they attract into the hydrogen sort of lets go of the last little hold that it had on the electrons with chlorine. So chlorine runs off as a full positive charge, and the chlorine hooks up with one of the carbons. This middle carbon now, you'll notice, has a positive charge. Well, carbon does not like to have a positive charge. I know it doesn't like anything because it has no emotions, but carbon rarely does positive charges. Now you'll see that in brackets I have the other possibility where hydrogen is going to grab onto one of those carbons. Which one is it? Well, in a way it's a coin toss, but on the other hand, there's that notion of if one possibility is unstable or less favorable, it's less likely to form. Okay, so let's take the one that we know is a little bit better at it, the one where the positive charge sits on the middle carbon. That, with a positive charge, is going to be attracted to a negative charge, that chlorine floating around with a negative charge. So now that carbon is the electrophile. It's the thing that loves electrons. So the chlorine, with its negative charge, is attracted to the positive charge of the carbon, forming the bond. That's it. That's all there is to it. And we know from class that that is the basis of Markovnikov's rule. Now, Markovnikov's rule just says that the carbon that has more carbons attached to it is more likely to end up as the carbon of the functional group. He said it a little bit differently, I guess. But the reason for that is back on that, in that first set of brackets. That carbon with the positive charge on the end is less stable. Now we can talk about or think about why it's less stable, but again, that's going to come down to how many carbons are attached to it. Those carbons that also have electrons that can sort of not really push in because there's no way those electrons are going to be able to move, but the positive charge can't really spread out, but it can be, I don't know, let's use the word softened a little bit by all these electrons that are nearby in the other carbon atoms. Carbon on the end doesn't really have that so much. I just had to figure out what I was doing here. Okay, if I take a look at the one where I was adding water, I had to have something else because water all by itself isn't reactive compared to hydrogen chloride. Hydrogen chloride we sometimes call hydrochloric acid. Water, we sit in it, we swim in it, eyes open. It's not very reactive stuff. So we had to add a catalyst to make it all happen. Catalyst was the H+. How does that work? Well, now the H+ is the electrophile. So carbon of the double bond pushes its electrons into the hydrogen. Carbon in the middle again ends up with a positive charge. Water now is attracted to that positive charge. I didn't put the partial negative, partial positives on this water molecule, but the oxygen has a partial negative, a fairly strong partial negative. It's going to hook into that, leaving the positive charge in the oxygen, which is kind of unusual and unstable. So the bond between the oxygen and one of those hydrogen breaks off. Doesn't matter which hydrogen, breaks off. Hydrogen floats away as an H+. So the original H+ that was our catalyst thing is now part of the molecule, but we get another hydrogen back. So technically, that catalyst does get consumed, but it gets reproduced or regenerated or put back in equal amounts. So as far as we can tell, everything is good. Now, by the way, there's no reason why the bond between the oxygen and that carbon couldn't break. But at that point, we'd be right back to where we started from, so we don't worry about that one. Okay, so a couple of examples of addition reactions. One is the one we just had. Now in this particular one, if I were to, I don't have Markovnikov's rule as a possibility because both carbons of the alkene, carbons of the functional group that's reacting, are exactly the same. They're both connected to two other carbons. But if I were to look at this one, where it's now a 3-carbon, I could either put the alcohol group on the very, very end or in the middle. Well, we know from class that Markovnikov's rule says it's going to go to the middle carbon as much as possible because the other one generates a carbon ion that just isn't very stable. So it's not going to form in that middle section of the whole reaction. Some of the examples in class we looked at had the possibility of isomers. When would you use isomers? Well, the answer is if the product has the possibility of isomers, then maybe isomers can happen. We're not going to get into how that happens or why certain ones do and other ones don't. We're just going to take it as if they're possible or not. If there is a fixed orientation, then what you will have is the possibility of isomers. If you have bond rotation, then it doesn't really matter if you draw it like as a cis or you draw it like a trans because there's going to be rotation around that bond. So if I take a look at this, I add bromine across the double bond, and I end up with a carbon-carbon single bond in between those two. Well, that carbon-carbon single bond can rotate. So I might draw this example as if it were trans, bromine on one side, bromine on the other side, but that's more just for convenience so that it doesn't look messy and crowded. There's no isomers there at all because free rotation around the bond. But if I start out with a ring, that ring can't rotate. It can flex a little bit, I guess, but it can't rotate. So if I were to add something across this double bond, then those groups that are added, or those groups that were already there, cannot rotate out of each other's way, or into each other's way if that were the case. They cannot rotate, so they're going to be stuck in that orientation. They're going to be stuck in that position. Then I can have cis-trans isomers. One of the reactions that we looked at was called ozonolysis. And ozonolysis is one that sometimes generates some problems because there seems to be a lot going on that we ignore. So we're going to take a moment and not ignore it. The first thing that happens when I add ozone, which is 3 atoms of oxygen, it adds across the double bond and forms this kind of weird looking complex thing. Then what happens is when I add zinc, now it's zinc mixed up with zinc powder, zinc dust, zinc granules mixed up in water. So you would stir it up and it would just be this muddy, slurry, gray looking sludge stuff that you wouldn't want to drink, but you dump that in. And what would happen is that would break those bonds as indicated. One of the oxygens would go to one of the carbons, the other oxygen would go to another carbon, and that third oxygen goes away with the zinc. So everything all works out. However, for our purposes, all we care about is this bottom line where I start with a carbon-carbon double bond and I finish with 2 carbon-oxygen double bonds. And depending on what I've got attached to those carbons of what was the carbon-carbon double bond, that will determine whether or not I end up with aldehydes or ketones or one of each. That reaction all by itself, in this example, really wouldn't be the best idea simply because if I were trying to make, let's say, the product on the left, what do I do with the product on the right? I've got waste. Now, it's possible that I can find some other use for the product on the right. So if I had a way to separate those two out, I could sell product on the left to one manufacturer or one person and product on the right to someone else. But as it stands right now, that's kind of limited because I end up with this big mess that I have to go through further separation steps for. But it's still a cool reaction. The last one we looked at was called electrophilic substitution. And electrophilic again, but the thing that is electron loving has to be really, really electron loving. It's also a substitution because the original thing stays intact. I'm not adding across a double bond, at least not by the time everything is done. I'm just substituting. Take one thing out, put one thing in. And it only ever happens with a 6-membered ring that looks like this. This is a benzene ring. And these things are highly, highly stable. Very, very difficult to get them to react. But some of the conditions that we had on that list, this is one of them. Now I want to emphasize this. I have a single carbon unit being substituted onto the ring. It could be a 3 carbon, it could be a 4 carbon, it could be multiple carbons to it. This is the one that just fits the best on the screen behind me. Okay, what happens? Well, first the reacting species, the single carbon unit with the chlorine, reacts with the catalyst to make this thing. And I want you to pause and look at that thing for a second because that's pretty weird. We just got finished saying that carbon generally does not do positive charges. That makes it quite reactive. So now the electrons in the carbon-carbon double bond of the benzene ring will be attracted strongly enough to the carbon ion there. That's going to move the position of the carbon charge, or the charge on the carbon, to this other carbon. Now that doesn't want to stay like that, so what happens there is that hydrogen that was still on the carbon, it's going to get thrown away, and the electrons from it get pushed into the bond. Now that hydrogen ion and that what's left over of the catalyst, they're going to get together, and the catalyst is going to regenerate back to, in this case, aluminum chloride, AlCl3. The hydrogen will connect with the chlorine that was part of that original thing as well. And then you'll get back to the products that are listed up there. Okay, hopefully that made enough sense that any questions that you still had after a little bit of practice will be answered. Again, I want to emphasize to focus on the functional group because that's what's reacting. So we need to pay attention to the functional group. Sometimes we need to look a little bit left or right of the functional group, but generally what's happening to the functional group. And we'll keep practicing.